1 plus I delta x. 1 plus, what's delta x? It's 1. So 1 plus I times 1 is 1 plus I. There's always going to be a substitution into your function of this little expression here, whatever it happens to be. You'll compute it first. We compute delta x, we know A. You'll compute this and put it into the function, 1 plus I. Delta x on the end is also 1. But I'm going to write delta x there. No, I won't. I'll try. So 1.
Where is the I from?
The I is from the formula itself. That is the counter, right?
Oh, okay.
In there. That's making sure that you're always moving up an increment of delta x before you compute the next area. So now, what is f of 1 plus I in our formula? Well, the function is x plus 1. So wherever I see x in that function, I'm going to put in 1 plus I, correct? You know what I'm saying or not?
Can you say that again?
I'm just, what's our function? It is x plus 1. That is this line. We're trying to approximate the area under this line segment from 1 to 6. Okay? So f is x plus 1. So I'm going to replace f with x plus 1. But what is x? X is 1 plus I. So I've got to put 1 plus I into here. So we'll read 1 plus I plus 1, which is 2 plus I.
Does 1 still add to the outside? Delta x?
No, you can get rid of that thing. I just want there to conform with the formula. You should see there's something happening. 0 to 4, 1 plus I plus 1. That's the function replacing x with 1 plus I. Okay? And then the 1 on the end I don't need anymore. It's not doing anything. So we now have, look. I understand. This is the most complicated process for having to add up, what is this? 2 times 1 plus 3 times 1 plus 4 times 1, 2, this rectangle has area 2, this has 3, 4, 5, 6. I understand that, right? I understand what each of the areas is. And this is a much more cumbersome process for this wimpy baby cakes problem. But what if I had to do 5,000 rectangles to approximate this thing? And this is going to be very handy, right?
You didn't put the 1 at the end because it's just 1, right? Like the multiplying one. I want to know if there's something.
No, you are right. That's right.
1.
Thank you for making sure that was clear there. But that's good. You are correct. Absolutely. No, I'm not kidding. You are right.
I mean, I don't want to miss out on some other time.
I don't win.
A number that's not
With
1.
me, there's no telling. You gotta keep track like that. You are absolutely right. You cannot risk it. All right. So now what we need to do is apply what we know about summations to this little expression here. Which is why I introduced the whole thing about the properties and formulae.
So you use the property of adding and subtracting.
Right. Look, you could plug in 0, 1, 2, 3, and 4 and just add those up. But I want you to start doing it in the way you have to do when you have more than 4 rectangles, and the problem is much more difficult to do great. Yeah.
How did you go from 1 plus I times 1 to 1 plus I plus 1?
That's not times. This is inside. That one's inside the function, and this is a 1 multiplied onto the function afterwards.
Yeah, it's multiplied.
It's not multiplied on the 1 plus I though. It's like this. It's like multiplied onto the function.
Yeah, but how'd you go from that to the plus?
Okay, so the 1 plus I is being put inside the function. So 1 plus I goes in for x.
Oh, okay.
So that gives us that, and I just discarded the 1 there because it's just, it's just a multiple of 1.
Would 2 just be your constant?
2 is a constant.
So you could pull that to the outside?
Can't pull to the outside. Multiplicative constants pull to the outside. This is additive. So what you do is you split this up using the additive property of summation. So you have sum of I plus sum of 2. Each of them still going from 0 to 4. Make sense? We're computing these rectangles in a roundabout way, which is more efficient for higher level problems. But I'm trying to demonstrate on a very simple problem. So now, what does this say? It says add 2 to itself 5 times, right? It's going 0 to 4. That's 5 2's. So that's 10, right? 5 2's added together is 10. And this says from 0 to 4.
Could you set I to anything if you wanted to? You set it to like 1.
Okay, so that's a good question. Our formulae were regarding what? When I started at 1, right? So you can change things
Because there's always going to be
want.
between that limitation, right?
So there's two ways you can do it. You can think and figure it out sometimes, or you can actually rewrite it. So if you rewrite this right now, I'm going to put it over here. Show you an intelligent option. Equals 0, I, 4, plus 4, 2. Raj would like for I to start at 1. Okay? Because our formula has to do with starting at 1. So what you can do is you can replace, you want I to start at 1, and what does that have to read in here?
1.
No, this thing has to start at 0, right? It has to start at 0. The first number out of this thing is 0, right?
Oh, it has to be n to the minus 1, right? So if you put a 1 there, it would be 1 minus 1, which would give you 0, right? So before it's an n minus 1? I mean, I to the minus 1?
Right like that. You can change the index if you want. You gotta make sure this starts the same. You can't be adding, you can't just say this, you can't just say that.
Yeah.
That's not true. Adding up 1 to 5 is not the same as adding up 0 to 4. But if you change it a little bit, I want to start at 1. So now this thing would start at 1. So how do I make it not start at 1? I'll subtract 1 from it. Now it starts in the right place. This starts at 0 like it's supposed to. It's supposed to start at 0. This starts at 1, which forms my formula. That's one way to go about it. Okay? Right? Plus, do the same thing here.
You
What's
have
going to
to
happen?
do that?
This is a constant, so it doesn't matter. No, we're doing it for the sake of seeing the formulas more directly. Huh? Yeah, yeah. Alright, so this is a little cumbersome. I would have just said, this is the same, adding up 0 to 4, right? This is 0, 1, it's the same as adding 1 to 4, because 0 doesn't count. What's that? The total is 5. One of them is worthless, right? So since this one starts at 0, which does not contribute to the addition at all, you could just change it like this, and that's much more efficient.
Why is it worthless?
Why is it this one?
Why was it worthless at 0?
Because the first value of the sum is I 0.
Oh,
So I'm adding 0 to it.
Okay.
So you can erase that in this case. Since the first term is 0, I can just bump this up to the next term. Right? Start at 1, which is the way the formula looks. So that's a more efficient way than doing this full index substitution here. I think this is obvious that adding up 2 5 times is the same as going from 1 to 5, right? You don't really need to change that. You just need to know the answer is 10 for that one. It's constant, it's not so difficult. So over here, though, you're adding up 1 to 4 now. So do you need to use the formula that we discussed, the very first formula we wrote? Not really. 1 to 4 is just the number 10, right? You played bowling before, right? So that's also 10. So 10% is 20. So there's our underestimate, 20. Okay? 20 what? 20 square units. Okay? There's no other information about the problem. You don't know what the x-axis or the f of x-axis stands for, then it's just square units. That's all it is. You don't have to write that. Just write 20. Any questions about the left-hand endpoint problem?
How'd you get 10 for the first part?
This is 1.